Alright, so here we're going to talk about feeding and fasting, and this is the first of these short videos that talks about the systemic response, neuroendocrine response to a change in blood glucose, and this is going to be feeding and fasting. So the process of digestion of a mixed meal yields glucose, amino acids, and fatty acids, and carbohydrates, fats, and proteins. And these products are digested and absorbed in a completely unregulated fashion. So much of what's in the small intestine is going to end up in the plasma. And then once they're in the plasma, they get transported to sites for storage. But each of these have certain energy properties that are shown in this graph. Carbohydrates, your predominant energy intake, and per gram they're about 4.1 calories per gram. Fats are twice this with 9.3 calories per gram, and they're your second most numerous calories that you take in. And then the proteins, similar to carbohydrates, but you take in less of those, and as a result, they're a smaller fraction of your daily energy intake. They have different storage forms. Carbohydrates, the circulating form is generally glucose, and it's stored as glycogen in the liver and muscle. You don't have much of this, but it's readily accessible and fast fuel, but you only have about 1 day's requirement in your muscles and in your liver. Fats are the predominant energy storage. You hold about 77% of your stored energy content as triglycerides in adipose cells. And then you have proteins, which are stored as muscle in general, and you have about 22% of your available stored calories as this. But obviously it's muscle, so it's functional, and therefore you're going to die before you can actually use it all. And so it's probably preferable to use glycogen or fats as your major stored energy source. The body has a capacity to interconvert all these substrates, and glucose is central to all this, which is probably why your body spent so much time regulating its concentration, as well as its long-term disabilities from having poor glucose control. But glucose sits in the center, and you can make glucose from amino acids, you can make it from the glycerol head group of triglycerides, and it's all broken down into ATP. The long chain of fats generally isn't converted into glucose, requires too much energy, and that's usually broken down into ketones by beta oxidation, and then this is fed into the energy requirements when fats are being used as stored fuel. So the next thing we talk about is what happens when you eat. How does the metabolic profile change? You'll eat something, and this is going to elicit a change in hormone secretion, and in general this will result in changes in insulin and glucagon concentrations. And so you'll eat, and your insulin will rise, your glucagon will fall, because your glucose concentrations in the blood will presumably rise, and then you'll get an increase in glycogen synthesis and a decrease in glycogenolysis, and so you get your stores of glycogen will then build. You have, due to the same hormone profile, triglycerides will begin to be formed, and lipolysis will be reduced, and protein synthesis is encouraged by insulin, and gluconeogenesis is discouraged, and then you end up with a positive nitrogen balance. In other words, your body will gain nitrogen, will gain protein due to the storage of proteins. And there's different factors that will stimulate the release of insulin. You have just the act of feeding will cause vagal stimulation to secrete insulin, Glucose increase in the blood and amino acid increase in the blood will stimulate insulin release, as well as gastric peptides, and then sympathetic stimulation, somatostatin, will inhibit it. But during feeding, obviously insulin release is promoted. So the incretin effect will increase your insulin release if you ingest glucose. Obviously this is a reiteration of the incretin effect, and then this shows a different representation of it that you've already seen. And so depending on what kind of meal you eat, you're going to get a different hormone response. And this selection of graphs shows you what happens when you have a high carbohydrate meal. Imagine it's just a sugary meal or a sugary drink. You get a rapid increase in plasma glucose, and as a result you get a large increase in insulin as well. And conversely then, the glucagon release is inhibited because you get such a large release of insulin. And so this is going to push all the glucose then into storage, into the glycogen stores, and if they're full, then it's also you get fats created and stored that way. When it comes to a high protein meal though, you're mainly going to stimulate the release of glucagon, but as we did say, insulin is also released. And these combination of releases sort of synergize in some ways and then counteract in others. So glucagon being released, that's going to stimulate gluconeogenesis, lipolysis, and glycogenolysis. And so a lot of the amino acids that come in then are going to be turned into glucose. And the insulin release then is going to try and store fats, store proteins, and store carbohydrates. And so this interplay then allows glucose concentration in the blood to be maintained, but the insulin is going to store some of the protein that's in excess as well. And also together with insulin secretion, a high protein meal is also going to stimulate growth hormone release. And so with insulin and growth hormone, you'll get storage of protein, or the anabolic formation of muscle. And then glucagon release is going to stimulate gluconeogenesis. So some of those amino acids are going to be released, going to be changed into glucose, but also you're going to get glycogenolysis. And so there's this balance here that will maintain blood glucose concentrations even when you have taken in a load of amino acid, because it's going to be created into glucose. You're going to have some glucose that's pulled from the stores, and this then will maintain your blood glucose concentration in respectable ranges. And then you have a mixed meal, and the mixed meal is going to vary. You could have a high fatty meal with some glucose, or a lot of protein and fats. And so this is just a representation of one particular type of mixed meal. You get an increase in insulin, but maybe glucagon won't be increased because perhaps you don't have as much amino acids. And this is just to show you that then with a mixed meal you get variable hormone responses dependent on the content of that mixed meal. And then this sort of summarizes what we just talked about. You get a carbohydrate meal, you get a spike in insulin, decrease in glucagon, a decrease in growth hormone, and this is going to put glucose into storage and facilitate its use. And so you'll clear then the glucose from the plasma. With a protein meal, you'll get an increase in insulin, although not as great, and you'll also get an increase in glucagon and growth hormone. So you're going to increase amino acid uptake, you're going to increase protein synthesis, but you're going to slow down glucose uptake and you're going to slow down glucose use. And some of those amino acids are going to get turned into new glucose because of glucagon being there. And so you get a kind of a mid-range effect. And then with a mixed meal you'll get an increase of insulin because vagal stimulation of eating will promote it, and then you may or may not get an increase in glucagon or growth hormone, but generally then it'll lead to glucose uptake, amino acid uptake, lipid uptake, and a lot of things with the insulin will generally drive things into store unless the mixed meal has an abundance of protein over the rest of it. It's always good to remember that the autonomic nervous system controls the release of insulin and glucagon. Increased sympathetic activity is going to reduce insulin release but promote glucagon release, and that will reinforce the actions of epinephrine. And then parasympathetic activity stimulated by the ingestion of food will encourage the secretion of both of them. So then we hit the post-absorptive phase. So you've had a meal and it's been digested, and now your blood glucose begins to decline because substrate is continuously being extracted from the circulation, and it's got to be replaced, or the plasma concentration is going to fall to a point where you start to feel stuporous or faint. You end up then getting decreased insulin secretion, increased glucagon secretion, you get substrate mobilization, lipolysis is stimulated, you get increased plasma glycerol, which can be made into glucose, and then increased ketogenesis, and your concentrations of ketones in your body will increase as they start to get used for muscle. Glycogenolysis will happen in the muscle and in the liver, and these will limit the fall in blood glucose. Obviously that's counteracted by tissue glucose use, and then together with substrate mobilization, cortisol will stimulate proteolysis, and you get increased plasma amino acids, and then you'll see this in increased blood urea nitrogen and increased gluconeogenesis in the liver stimulated by glucagon. At the end of an overnight fast, about 75% of your glucose sources will come from glycogenolysis, so you'll be drawing from stores predominantly, but about 25% of your glucose will come from new glucose from lactate that's released from the muscles, or 25% of that then it comes from a breakdown of the muscles. Some of this new glucose is created from glycerol, and a very small amount comes from pyruvate. And the utilization of these glucose substrates at the end of an overnight fast is mainly by your CNS, 45% of that, and 25% by your splanchnic organs, 20% of glycolysis by muscle and blood cells, and then 10% is oxidization in the muscle. So what happens when you don't eat for a long time then? The primary stimulus that drives the endocrine response in the post-absorptive period is a decline in plasma glucose. And this stimulus decreases the rate of insulin secretion and plasma insulin, and increases the rate of glucagon secretion, and therefore the plasma concentrations of glucagon. And here we see it in a 3-day fast. Your glucose levels begin to drop, and insulin then falls away, and glucagon starts to rise. You'll see during a 3-day fast how the different substrates begin to alter. Glucose decreases, as we just saw, insulin decreases, and glucagon goes up. And then consistent with that, or in line with that, you get an increase in beta-hydroxybutyrate as ketone bodies start to appear. Lipolysis is increased, and so you see free fatty acids starting to appear more. And glycerol is then increased as the free fatty acids are broken down into their metabolites. You see alanine begin to disappear as it's used as a fuel source to create new glucose, and then there are branch chain amino acids that appear as proteolysis is encouraged in the absence of insulin. And so this chart then shows what happens over a 5-day period to different plasma concentrations of metabolites and hormones. So glucose, as we know, decreases, and insulin decreases at the same time, and glucagon is then encouraged and stimulated by the low blood glucose. Cortisol, to the most extent, is maintained, but most importantly is that to note is that growth hormone is increased, and so the effect of this then is to inhibit proteolysis, and so we begin to see the metabolism shift away from using protein as a substrate and moving on to stored fats to as a main fuel source. And you'll notice that levels of T3 begin to decrease as the body tries to conserve energy without it actually taking in any. And so glucose is reduced, although after a while it stabilizes and remains consistent for a remarkably long period of time. Insulin decreases and glucagon increases and then is maintained over the period of the fast. In general, protein turnover is reduced under this situation. Not only is growth hormone released to protect the muscles, but also as plasma ketone levels increase, you get the inhibition of proteolysis as well. So both of these mechanisms will prevent the excessive degradation of proteins. And so you see here how ketone bodies will rise. Beta-hydroxybutyrate increases greatly over the first 10 days, and the use of alanine decreases over time also. So this chart then summarizes what happens during a long-term fast as far as the neuroendocrine system goes. So you have decreased blood glucose, that's going to decrease your insulin plasma concentration, increased growth hormone, maintained cortisol, and decreased T3 and T4. So the increased growth hormone is going to slow your muscle proteolysis, you're going to decrease plasma amino acid, and decreased gluconeogenesis, which is obviously going to take away from the plasma glucose. But part of this is through growth hormone and part of it is through the increase in plasma ketones. So that there is another energy source to replace the plasma glucose. The decreased insulin is going to decrease glucose entry into cells and decrease the glucose use by the cells. This is going to put less of a strain on the plasma glucose. T3 levels dropping is going to decrease your overall metabolic rate, and this is going to help maintain plasma glucose levels by lowering the demand. And then increased triglyceride mobilization through increased glucagon and maintained cortisol will then increase plasma fatty acid concentrations, increase liver ketogenesis, and then this is going to increase the plasma ketones, and obviously the central nervous system can use this as a source of energy, and this is going to decrease the glucose use by cells, which is then going to help maintain plasma glucose levels. And then your increased free fatty acids and ketones that are used by cells will also contribute to this decrease in glucose use.